All right, this is just a quick video to help you understand how to use a couple of shortcuts when it comes to multiplying, dividing, and taking powers of complex numbers. It's really helpful if we can put them into trig form. So you'll notice here we've got u and v that are both trig form complex numbers. 3 times the cosine of 30 degrees plus I the sine of 30 degrees, which remember we also often write sort of as a shortcut already as 3 CIS, cosine plus I sine of 30 degrees. We also have vector v here that's 6 cosine 45 degrees plus I sine 45 degrees. So also again could be written as 6 CIS 45 degrees. If we want to multiply two complex numbers, the nice part is there's a shortcut where really all you need to do is multiply the lengths of the distance to those complex numbers. So essentially, much like the magnitude of a vector, the distance from 0 to this point in the complex plane. Again, that's what 3 and 6 already stand for. So we're going to multiply those two things. But then all we have to do is add the angles. It relates to our sum and difference formulas, and I'm sure you can look up a proof, or if you check the class notes, there should be a proof up that just shows you that we can just add those two angles, and it basically is a shortcut for multiplying those vectors. So if I want to multiply u times v, I can just take 3 times 6, then say CIS, and add my angles. I don't actually have to FOIL together, if I imagine multiplying this by this, foiling together all those trig functions, because again, it's sort of a shortcut that you will end up with 18 CIS 75 degrees, and I guarantee you'll get the right answer that way. Division works essentially the same way. U divided by V, I'm going to divide my lengths there, or divide those essentially magnitudes, CIS. But now, much like exponent rules, when you multiply, we add our exponents. Well, when you divide, we used to subtract our exponents. Very similarly, when you divide two complex numbers, divide their lengths, but subtract the two angles. So the first angle, or u, the angle on top, minus 45 degrees, or the angle from the second number, or v. And you'll basically get 1/2 CIS negative 15 degrees. And again, you could always convert that back to standard form by actually finding half the cosine of negative 15 degrees for the real part and half the sine of negative 15 degrees times I for the imaginary part. Now, if that's going to work for multiplying and dividing, it actually also works for powers. And this is what we call DeMoivre's theorem. DeMoivre was a pretty famous mathematician, and he came up with this theorem that basically if we're going to multiply two things, I can just keep multiplying their lengths. Well, that's the same as just taking the power of that, depending on how many times you want to take the power of, or how many times you want to multiply this complex number by itself. So if I want to find v to the third, first step I'm going to take is 6 to the third. But much like, again, our shortcut for multiplication, if I'm just going to add its angle to itself, right, multiply, or v to the third power multiplied by itself 3 times, I can actually shortcut that by saying 6 to the third CIS 45 times 3. I can just multiply it by adding 45 to itself, 45 plus 45 plus 45, or 3 times 45. So you'll end up getting 216 for 6 to the third, CIS 135 degrees. And again, you could also look up the cosine at 135, find out that it's equal to negative root 2 over 2, comma. Sine would have been, and so actually instead of a comma, let's go ahead and put a plus sign, because we would be adding that on to I times the sine, or root 2 over 2, sine of 135. And then don't forget to multiply by 216 in front. So if you wanted the standard form of this, I can reduce that down. That would be negative 2 divides into 216 as 108 root 2 plus I, the sine of 216 times that. So essentially, again, 216 times root 2 over 2 is 108 root 2. But don't forget the I, telling you that that's the imaginary part of that function. Again, keep an eye on the directions. Most of the time we can just leave these in trig form, But if the directions ask for standard form, you should be able to convert back to standard. U to the sixth actually will work out well in that form as well. We'll take 3 to the sixth CIS, our 30-degree angle, times 6. We'll notice that that's really just 729, again, 3 to the sixth power, CIS 180 degrees. Well, cosine at 180 degrees is -1. So basically we get negative 729. We'll write this out for you here. So we've got 729 times, again, cosine would be a -1, plus I, the sine of 180 degrees. Well, sine of 180 is just 0. So essentially that disappears, and -1 times 729 is really just -729. Go ahead on the next page here. I've got a vector written out, or a complex number, sorry, written out, so that you can practice finding that complex number to the third power and to the seventh power. Rather than actually foiling out this thing times itself and then times itself again, remember, if we can put this into trig form, so the very first step I'm going to do is find r and theta. If we can put that in trig form, though, then I can take advantage of DeMoivre's theorem to find the powers. Go ahead and pause the video now. Attempt finding the radius and theta, or the angle. Once you find those, I'll start the video back up again here in a minute with those filled in so you have the right numbers. Then I'll pause the video again and we can attempt DeMoivre's theorem. All right, here are r and theta for you. So make sure you got the same numbers that I did. Then again, pause the video again and you can attempt finding DeMoivre's theorem. All right, so here are both answers for you. Basically, again, we're going to take r to the third power. Then we're going to multiply our angle by 3. So 2 to the third becomes 8 CIS, or cosine plus I sine, of 135 degrees. That's our trig form. Again, same thing worked for the seventh power. Kind of did the same idea. We got our 128 CIS, cosine plus I sine, of 315 degrees. Now, the directions asked us for both trig and standard form. So then again, find your cosine and your sine, multiply by your number in front, and you should get those answers to the right. I hope that worked out well for you. Last thing I've got for you is just an example of why in the world would we want to know this, or where might you see something like this in the real world. So if we took that same value, root 2 plus I root 2, and took it to the nth power, n being squared, and third power, and fourth power, and fifth power, you'll end up getting 4i when you square it. We already found out 3 was -4 root 2 plus 4i root 2. Taken it to the fourth, and the fifth, and sixth, and seventh, and eighth, and again, we already found the seventh power as well. You'll notice that the number in front just keeps getting sort of larger and larger. And if we plot these on a graph, oh, sorry about that, bell went off there. If we plot these on a graph, you'll notice that if I go over 4 units, and I'm going to count by 4 is really small here. If I go, the first one would have been root 2, so you're going to kind of be really close to the origin. But then I'm going to be 4i, so directly 4 units up. Then I'm -4, 4, so I'm kind of directly across from there. Then I'm out at -16, so here's 4, I'm going to be kind of way out this direction. Then, kind of kitty corner to that, -16, -16. Then I'm way out at 64, and we kind of imagine it's way down here somewhere. And then another one here, and then 256 will be well off my graph. But you'll notice, again, we're getting farther and farther from the origin, but we're also going from 45 degrees to 90 to 135, essentially another 45 degrees each time, which basically ends up making a nice spiral. And anywhere we would see spirals in the real world, such as on coneflowers, if you follow the seeds, you'll notice that nice spiraling curve of seeds. Right? There's lots of spirals actually kind of tying in together. If you follow the seeds, they actually lay in a nice spiral. Or you can maybe think of a snail shell or a nautilus that would kind of spiral out that way. Basically, we just follow that spiral, and that's where one place you would see this kind of idea in the real world. It's a way to model that spiral. Right? I hope that helps you again with complex numbers and finding their powers or multiplying and dividing them. Enjoy and good luck.